In this class, we are going to talk about information processing, memory, and data encoding in sensory systems. This class and next class we'll do that. This class will talk about the visual system. Next class we'll talk about other sensory systems. We'll talk both about how information is processed in human brain with respect to these sensory modalities, and then we'll talk about the engineering applications, both in terms of processes. In case of visual processes, for example, we'll talk about how you can help blind people or visually impaired people see and therefore perform visual tasks and navigate their world better. And we'll also see the other way engineering applications. That is, from our understanding of how brains function, we will look at how that information can be used for understanding and better designing artificial vision, computer vision, robotic vision, and those kinds of applications. So we'll first start with what an eye looks like. You have the 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 light passing through the cornea and the lens that finally is incident and focused on the retina. Retina has the light sensitive machinery. So when the light comes in onto the retina, it's kind of designed counterintuitively. If you were engineering a device that was doing visual information processing, you would put light sensors directly when the light comes in, right? But instead, in the eye, it passes through the nerve layer that passes information to the brain from the eye, passes through ganglion cells, amacrine cells, bipolar cells, and horizontal cells that that process visual information, and then finally it hits the rods and cones, which are the light sensitive cells in the eye. Rods respond to all wavelengths of visible light, whereas cones respond to specific wavelengths. So red cone will be most sensitive to red light, green cone will be most sensitive to green light, blue cone will be most sensitive to blue light, and so on. So rods and cones are very fiduciary kind of responders. That is, they will reliably tell you when light is incident on them. And counterintuitively, these rods and cones are active firing action potentials when there is no light incident on them. But when there is light incident, they will shut down. Uh, and that helps you precisely time when the light is incident on the eye. When that information passes now to the processing machinery within the eye, however, it's not simply passing on presence or absence of light. What it's doing is center surround processing. An on-center ganglion cell, for example, will report when light is incident on this particular cone, but not incident on its neighbors. So it's going to do center surround. Light is present here, but not here. That's what this on-center ganglion cell will tell the brain. If this ganglion cell is instead off-center ganglion cell, then in that case it will tell you when there is no light in the center on this cone, but there is light present on the surround, right? So therefore these cells are not simply reporting presence or absence of light, but they're processing that presence or absence of light to create an image of contrast. When there is a difference in light being sensed by the neighboring cells, that's when there is maximum activity of these ganglion cells that will get passed on to the brain. Other couple of things that you need to notice is there is this part of the eye called the fovea, where there is a highest density of these cones that enables to see with highest possible resolution. And then as you go farther and farther away from the fovea, the density of rods and cones gradually decreases. The cables have to pass through. The cables, you remember, are coming out at the uh, in the inner surface of this retina, but then they have to pass out before they go to the brain, right? The brain is back here. So there has to be a hole in the eye through which all this cable passes. So that particular hole over there does not have any kind of light sensitive cells. There is no space for light sensitive cells, and there is also blood vessels and all. So all the plumbing of the eye, the wiring of the eye is passing through that particular spot. So there is no information being received. But you don't walk around the world seeing two blind spots corresponding to two of your eyes, right? You see the world as being a continuous existence. So what's going on here? So let's see what's going on here, right? Your eye is doing something called perceptual filling in. So let's see what that means, right? You see that cross? Close one eye, focus on this on that cross with the other eye. Put your finger right in front of you, staring at that cross, and then such that your fingernail is right at the cross, and keeping that fingernail right at the cross. Now continue looking at the cross, but move your fingernail slowly farther and farther away till it gets to a point where you'll suddenly notice that you're no longer seeing your fingernail. Uh, for the purpose of this demo, I'm going to simply move my finger, uh, keeping it in. But at certain point, you're going to notice that the fingernail is not visible, but your finger is visible. That is your blind spot. That is the spot at which your cables, your plumbing, right, blood vessels and so on, is passing through, and therefore there is no light. There is no light sensitive neurons in there, and yet you're not able to notice that blind spot normally. Only when you do this particular exercise to find the blind spot, you're going to be suddenly able to find the blind spot. So what is going on over here? Uh, what your visual system is doing is uh, is trying to give you a sense or sensation of your world being continuous. There not being holes in your world, because you know from real life that there are no holes in the real world. So if you start seeing holes in your visual system, you'll start losing bits of information, right? So you're filling in, knowing what you know about the information that is available everywhere else. You're filling in. So for example, I am seeing my finger, right? And therefore I am seeing my fingernail as well. I know that my finger is not cut at the fingernail, and therefore my fingernail needs to exist. So even when that fingernail is in my blind spot, it is going to be uh, perceived as being visible to me. Only when I'm forcing my system to acknowledge by closing one eye and then putting my fingernail specifically in my blind spot and sort of paying attention to what is going on over there, that's when I start noticing that my fingernail is no longer visible to me. Uh, so perception that is happening in your visual system is not the same thing as honestly reporting whatever light is sensed by your retina. There's literally missing piece of information that your visual system is actively filling in, right? So why is your brain fooling you? Why is it important, right? So if you look at a whole bunch of these examples, you'll see why it's important, right? When you look at this particular scene, for example, this is just a bunch of lines and squiggles, right? There is no landscape over here, and yet you have no difficulty in figuring out there are birds flying, there is sun that has just risen, there are mountains, there is a road, there's a truck driving on the road, there's a little pig over here, there is a house, a tree, and so on, right? But all that you're really seeing is squiggles, right? Little bits of lines, but knowing what you know about the world and processing that information, you can very easily tell that that's what that scene is. It's hard for a artificial vision system to say that, oh, that's what this complex scene is, uh, without like constantly being trained on labeled data set with humans telling it that this is what this scene is, this is a truck, this is the sun, this is the house, and so on, right? Without that, your artificial systems can't look at actual photographs of real world and interpret those actual photographs of real world as uh, as these simple line drawings. Um, uh, you have this cube illusion where you can have, is this corner in front or is this other corner in front? And you can continuously keep flicking back and forth the image, right? When you're looking at it. And that's happening because there is incomplete information and your visual system is trying to make the best guess possible of what that incomplete information is. Uh, Again, your artificial system is not going to be able to do that because the complex perceptual machinery that is there in your visual system is not there in your artificial system. Uh, Here in this illusion, you can either see two faces or you can see the vase that is in between these two faces. And even when you know that this is simply an illusion, you can keep flicking back and forth consciously now. Once you know what you're looking at, consciously you can keep flipping back and forth between the vase and the two faces. I'm not going to tell you what's there in these two images, but observe it very carefully and come and tell me in the class what you saw. Again, extremely conflicting, confusing, and degraded kind of information that is present. And despite that, once you know what you're looking at, that image uh, uh, completely hits you in the face every time you look at it. It's very, very obvious what you're looking at. And your visual information system, information processing system, does this kind of information processing with a lot of ease. Uh, it helps you sort out things in contrast, right? If you've walked from sunlight to shade to indoors tube light, right? Fluorescent light, incandescent light kind of situation, you'll you'll notice that yeah, colors appear slightly different, but you're still able to tell when you're seeing blue light, right? When your shirt is blue, it appears blue whether you are seeing it in sunlight or where you are seeing it in fluorescent light indoors. But uh, but that kind of distinction is hard for computer vision systems. So, for example, here is an artificially generated example that shows you this kind of difference, right? So these two women in these images, you can very clearly make out that the dress is black and the apron and the frills that this one is wearing uh, is blue, and this other one, the dress is yellow, but the apron is white, right? uh, and it looks like, yeah, there's some sort of a yellow filter being applied on part of this image and some sort of blue filter being applied to some part of this image, but you can say that this is white, you can say that this is blue. But when you actually carefully look at this thing continuously, this color is exactly the same as this color. So if you were doing simple sensation task that your artificial vision is very good at, then you'll see both these locations, this spot and this spot, as being blue spots. Whereas if you're doing perception the way your visual system does, and this is the perceptual problem that your visual system needs to solve, right? Regardless of the context in which you are standing, your visual system needs to be able to say, I am wearing a blue dress or I am wearing a white dress, and so on, right? or you can say black versus yellow in this particular case. Same thing. In this context, you see this as a black dress. In this context, you see this as a yellow dress. But when you actually see what's going on over here, it's exactly the same dark yellow kind of light that is getting emitted at these 2 points. So your perceptual system is doing something much more nuanced than a simple sensory kind of representation. Here is another example. If you look at these tiles A and B, you can very easily make out, oh, A is black or gray and B is white, right? But when you look at these things carefully, you'll notice that B is a white tile that is in the shade of this cylinder over here. Now, if you look very carefully at A and B, uh, uh, just for illustration, these things have been covered, rest of the things have been covered. So you can see that A and B are actually light at exactly the same gray intensity. But because of the context that there was a shade over here, B appears to be white while the A appears to be gray. um, and you can actually go back on the slideshow and actually focus only on the B tile or the A tile, and you can convince yourself that it's actually the same intensity of light that is coming out of B as well as A. But because of the context that B is in shade, it appears to be white uh, as against A appearing to be dark. So perceptual systems are doing something much more interesting than simple sensation or honest representation of light that is that is incident on your camera, right? Um, so so as the information processing gets to higher and higher levels of this perceptual system, you start doing more and more complex perceptual decisions. So, for example, in the primary visual cortex, don't worry about the names of these regions. In the primary visual cortex at the back of your brain, uh, you have neurons that respond to lines of light. That is, if this line is vertical, there will be some neurons in your brain that will respond to this vertical line. There will be other neurons that respond to horizontal lines, and then yet other neurons that respond to lines at different angles, right? Now, those neurons in the primary visual cortex will respond only to these lines at different orientations. Okay? But when you go to the secondary visual cortex, now something very interesting happens. It starts responding to perceived shapes and contours rather than shapes and contours that are actually present in your stimulus. So here are some examples of that, right? So here you can very clearly see this triangle. The white triangle is right on top of a black bordered triangle, right? But in reality, there is no such thing. There are these pairs of lines, 3 pairs of lines, and then there are 3 Pac-Men, right? But you perceive this as complex shapes that don't exist in this image, but perceptually those are the things, because that's what you expect to see when there is a white triangle on top of the black border triangle. Same way over here, you are perceiving line in this case, but no line in this case. And the only difference over here is that the circle here has been cut at 2 points that are collinear with slits in these black circles over here. Here, on the other hand, there is no opening in this middle circle, and therefore you don't perceive this as a continuous line. Here, for example, you have just a set of horizontal lines. In the primary visual cortex, you'll only see responses to horizontal. But uh, but when you're perceiving this, you're actually perceiving more strongly this kind of wave-like contour over here. Same thing over here, you perceive line, and you perceive line with vertical lines with more and more confidence as the number of these horizontal lines keep increasing, right? But when you look at the primary visual cortex, area V1, you'll see only responses to the lines that are clearly visible, that are actually there in your image. So for example, primary visual cortical neuron will respond to just this vertical line. It will not say that this line is vertical over here. But when you look at secondary visual cortex, area V2, you'll have neurons that respond to these horizontal lines, of course, but you'll also get a vertical line response. And that vertical line response will be present when you show this vertical line, as well as when you show this illusory contour that is creating this illusion of there being a vertical line. And in fact, the response to this illusory contour is much stronger in area V2 than the actual vertical line over there. Similarly, if you look at this illusion, as you increase the number of these horizontal lines from 2 lines over here to 3 lines, right? Line 1, line 2, line 3, then to 4 lines, 1, 2, 3, 4 horizontal lines, and so on. Your perception of this vertical line gets stronger and stronger. And correspondingly, if you look at the secondary visual cortex, you see that response to the visual stimulus, the perceived vertical stimulus increases with the number of horizontal lines that contribute to that perception of vertical line, right? So as your information is getting processed in your visual pathway, uh, you're not simply passing on same bit of information, but you're throwing away much of the available information. You're throwing away information about, oh, there are so many lines, right? Unless you're specifically focusing and looking at these lines. You're simply saying that, oh, there are these bars that are very clearly visible, vertical bars that are clearly visible over here, or there is a wave clearly visible here, there's a triangle here, and so on. Right? That kind of information is getting passed on to your higher and higher order system. So that will help you perceive shapes, that will help you perceive objects. This is a dog, that is a cat, that kind of distinction that we've been talking about, right? As information gets processed in your visual system, you're going to get that kind of perception. Perception also is dependent on your ability to predict, right? So for example, here is a clock hand that is going around in circles very rapidly. And when the clock hand is at this particular position, you can predict clearly that it's going to rotate and keep moving, right? But look, what's happening is every now and then there are these flashes of a line that is farther away from this rotating clock. If you look at it carefully, what you'll see is that it appears that the line flashes slightly behind the clock hand every time, right? But if you manage to actually pause the video at exactly the right point, you'll see that the two lines are actually perfectly coincident for that transient image where that longer line pops out. And that's happening because your visual system is predicting the clock hand rotation, whereas flash of light is not being predicted because you don't have any a priori motion expectation. That flash of light is just showing up at that particular spot. So your predictor is actually moving ahead of the actual perception. So you get perception both in terms of two-dimensional space or three-dimensional space, and in terms of predicting what is going to happen in the future. Uh, so here is what we understand about perception, right? Perception is an active conscious process. It is heavily influenced by the context, expectation, right? The clock arm is going to keep turning, for example. Memory of the scenes that you've seen in the past, and so on. Here is a dog, that's a cat. I saw a sunrise, this is what sunrises look like, and so on. And then what sensory inputs are available. Perception can fill in the gaps in sensory inputs. You saw blind spots, you saw literal line drawings and made out complete landscapes from those line drawings. you made up much more complex scenes and so on, right? From simple illusory contours. So, so your perception can fill in all kinds of gaps in the information, visual information that is available to you. Then your perception is also about ignoring irrelevant details as it is about recognizing important patterns and events that you need, right? I need to understand what a dog is shaped like. I don't really care that there is a line this way and then line that way. I need to perceive that entire contour of a dog and then recognize that this is a dog, right? So it's about ignoring irrelevant details. Your dog might have played around in dirt and now might appear brown, but you'll still recognize it as your dog, not as, oh, this dog is different from the white dog that I used to own, right? Um, so your perceptual system needs to be able to fill in details, ignore details, and so on. So your visual system, as you can see, is able to do really, really complex information processing. Uh, we'll quickly look at uh, the visual information processing pathway, right? Your eyes are reporting center surround kind of representation, presence of light in the center and absence of light in the surround, or absence of light in the center and presence of light in the surround, and so on. But there are two parallel pathways: the magnocellular pathway that represents motion, right? Not just presence or absence of light. Which direction is this presence and absence of light moving? Parvocellular pathway, on the other hand, it represents the shapes much more accurately, and that information remains more or less segregated in the visual system as it passes through the lateral geniculate nucleus of the thalamus, the primary and secondary visual cortices, and then finally it gets segregated to motion sensitive areas, the area MT and posterior parietal cortex, versus uh, uh, inferotemporal pathway that recognizes shapes, colors, and so on, recognizing objects and things like that. So if you're trying to catch a ball, uh, uh, your uh, motion perception is going to be very important. When you're going to trying to distinguish that ball from a flower, your uh, your ventral pathway is going to be important. And obviously these pathways are not completely independent of each other. They are talking to each other, but their primary functions are different from one another. When you look at the visual information processing, it's really, really complex kind of network, right? Around 1991, Feldman and Mishkin reported of the order of what, I forget the number of areas, but dozens of different parts of the brain that are involved in visual information processing. Now people have identified hundreds of areas. Some of these areas, people have demonstrated that there are subregions that do different functions, and people have demonstrated newer areas that are involved in visual information processing. Other thing that you'll notice in this system is there are loops within loops within loops of information processing. It's not a simple feed forward information going from I to the higher order information processing regions. Um, and and the kind of perceptual decisions that you saw you're capable of doing are enabled by this kind of complex information processing machinery. Okay, so now that we understand what kind of complex information processing you can do, you can now start talking about visual processes. So let's start with why do we need visual processes, right? If people are born blind, they suffer damage to their eyes, suffer damage to the visual information processing machinery from optic nerve to different parts of the brain that process information and so on. They may not be able to see. Or may not be able to see with high enough level of accuracy and so on. So you can create visual processing uh, uh, devices, right? So you can do visual processes with a camera capturing the image. Uh, 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 that image gets processed, And once it's processed, it is transmitted to a transducer that passes on information to your nervous system. Now, these transducers can be located within your eye, it can be located on the optic nerve, or it can be located on the cortex, right? You can do stimulation at different levels in order to pass on the information to the brain. So, for example, when you have diseases that lead to damage of your light sensitive cells, your rods and cones, but keep the rest of the visual machinery intact, you can simply uh, uh, put a small chip in your eye that uh, uh, you can put a small chip in your eye that can now do that can have multiple electrical points of contact such that when you stimulate them independently and individually, you can create perception of vision in your retina itself, right? Presence and absence of light, remember? And you can create all these centers around and those kinds of perceptions. So people have uh, experimented with variety of different kinds of devices, and these devices are able to help blind people with some level of uh, uh, differences, right? So you can, when the light gray bar shows when the device is active versus when the device is not active. These people can distinguish between different shapes much better when the device is active as compared to when the device is not active. They can distinguish where the shape is, what is the shape, right? Circle versus triangle versus square kind of differences. uh, they can tell you how many tables are there, where the tables are, and uh, is this a table? What is this object? Is this table? Is this chair? That kind of thing. Right? And you can see the performance is kind of degraded when it comes to recognizing what is this shape, what is this table, and so on. But still, it's better than nothing. Uh, Unfortunately, these kinds of prosthetic devices also show degradation over a year or so, right? So therefore, they're not that very popular. So biocompatibility of these kinds of devices is a topic that needs to be worked on so that you can prevent degradation of what is going on. But see, these are still very crude kind of perceptual tasks, right? When you start talking about clock, what is the time that the clock is showing? Vast majority of the people can't make that distinction even when the prosthetic device is on. When it comes to recognizing letters, even big letters that are written rather than small print that you can easily read, the big print like this headline visual processes that is written over here, very small fraction of people are able to read those letters, right? So high acuity vision is not possible with these kinds of prosthetic devices. So right now there is a lot more development that you can do in order to engineer devices that can see much better than these devices, right? Now we can go the other way around also. So in the previous slides, you saw examples of how you can augment vision that is damaged, blind people or uh, people with lower visual acuity, how you can help them see better, right? Now we can see, knowing what we know from the visual system, how you can help your uh, uh, artificial uh, devices, right? Drone vision in this particular example, but you can do computer vision, you can do robotic vision, and so on. So people have come up with de novo algorithms, right? Completely artificially engineered algorithms to see. But those algorithms, as we saw in the previous talk, as we saw that those are highly energy inefficient. They require a lot of information to be available a priori and things like that. Can we improve performance of these systems, right? So you remember that when we are talking about neural systems, the one major distinction is spiking neural networks, right? Neurons fire action potential, and transiently in a brief period of time they pass critical information but when they are not active, they are really not passing any information. And you can do very well timed, very precise, and very rapid information processing in these kinds of systems, right? So you can help that by using something like event-based camera rather than frame-based camera. So frame-based camera will, at a regular interval, keep acquiring frames one after the other. Event-based camera will acquire only when something happens, right? When there is flash of light, when you trigger it with sound or with electrical impulse at particular time, and so on. When that information comes in, you can pass it through an analog neural network in order to process that information. So you can get graded kind of responses, and you can do a variety of complex processing. So this is what your standard computer vision kind of processes do, right? But if you introduce spiking neural networks in there, either independently on their own or in combination with these analog neural networks, then you can do something much more interesting, right? Inputs coming in can be still graded, but only when that graded input adds up to a certain minimum threshold activity, your leaky integrate and fire neuron can be made to spike, and only when that leaky integrate and fire neuron spikes an action potential, you pass on the information to the next level, right? And you can have these networks. So you can create either hybrid or sensor fused spiking neural networks, artificial neural networks, and so on. And then you can process information. You can use the standard CPU, GPU kind of hardware or dedicated hardware, FPGA, field programmable gate arrays and things like that. Or you can actually create these neuromorphic computational devices that model activities of spiking neurons, right? And create combinations of all of these in order to create visual things. So your drones now will be able to, in real time, figure out optic flow, how fast is the image moving, depth, how far is a particular object. You can segment your image uh, into different contours. Within those contours, you can figure out this is a tree, that is a road, that is a building, and so on, right? So all this kind of thing can be done much, much better when you understand your natural visual system and then apply that understanding to the kind of devices, artificial vision devices that you engineer. When that information now comes, we saw how that works in the visual system, right? Retina, lateral geniculate nucleus, and then different visual cortical regions and so on. You're going to see some similar kind of information processing in your auditory system, in your somatosensory system that responds to touch, and then your olfactory system and your taste system, right? Um so and then we'll also look at engineering applications, but we'll do all those things in the following class.